Hope all of you are doing well. My name is Shriya Bansal and I'm currently working as a software engineer at Microsoft. So now in this video, after having already talked about the small pieces that are required to understand banker's algorithm, that would be understanding all the data structures such as the available matrix, which tells you how many resources or what resources of which resource is available or what instance of resources are available. Then maximum matrix, which was an n cross m matrix, designating or telling us that for a particular process, how much instances of a resource can it ask for. Allocation means how many instances of a resource has been allocated to a process, and the need matrix basically was how much more of the remaining resources for a process are still required. Okay, so that's what pretty much the overall idea was for all these four aspects of banker's algorithm. So now we can move ahead and actually talk about the two algorithms which banker's algorithm basically comprises of. And then we are going to take all the examples to understand this concept in great detail. So the first algorithm is the safety algorithm. This algorithm basically finds out whether or not a system is in a safe state. Okay, if you remember the concept of deadlock avoidance, there the concept of safe state was that if a system is in safe state, that means it cannot go into deadlock. Okay, so what we do is we first find out whether when we allocate the resource, whether the system is still in a safe state or not. Hence the name safety algorithm. Okay, so let's say we have work and finish, okay, to be two vectors of length m and n respectively. Okay, and initially work is equal to available and finish of I is equal to false for all the processes. So here, wherever we talk about the safety algorithm, what we do in the first idea is that, remember, there are n processes and there are m resources. Total m resources are there. Okay, so what happens over here is we basically make work is equal to available. Available was basically having the number of instances for every resource which is available. Okay, so here the length of work is also m. Okay, and secondly, what we had over here was we do finish of I is equal to false from I is equal to 0, 1 to n minus 1, based on if you're following 1 based indexing or 0 based indexing. What it means is that initially no process is finished. Okay, that is why no process is finished. That is why finish of I is equal to false. Okay, the length of finish is n. That means we have an index for every process. Since all of them have false, that means no process has been finished. Whenever a process is finished, we will basically mark that index to be true. Okay, and work is equal to available means that in the start no process is finished and all the resources are available. So that is why work is equal to available. Okay, then the second point over here in this algorithm basically is that we basically find a process, find an I such that finish, this is H, such that the finish of I is equal to false. Okay, we need to find a process which is not finished. If it is not finished, that means it needs to be executed. That means the finish of I would be equal to false. Okay, and secondly, right, the need of I would be less than work. Okay, that means we need an unfinished process. Okay, and that process can be satisfied also with the available resources. Okay, so what we do over here is we basically find an I such that first of all finish of I is equal to false. That means that particular process has basically not been finished, and also the number of resources, okay, its need is a matrix, right? Here for every row we have, let's say, resource R1, R2, R3 and R4. Whatever you need in the as the instances of resources, it should be less than or equal to the available resources. Okay. In English, what does it basically means is we basically need to find an unfinished process. Okay, first we need to find an unfinished process whose need can be satisfied with the available resources. Okay. Now the third one that we have over here, right? Now otherwise we simply go to step 4. So here, if this is not satisfied, go to step 4, which we will come later. Next is step 3. What happens in step 3 is that if you are able to find such a process, okay, what you will do is you will do work is equal to work plus allocation of I, right? Because now you are allocating, and then since the process is marked finished, right, you basically move ahead. That means the meaning of this is when you actually find an unfinished process, the resources are allocated and the process is basically marked as finished. Okay, so here in the work you are basically saying that whatever work you have so far plus the allocation that you have done. Okay, what was allocation over here, if you remember? Right, allocation was basically defining the number of resources which has been allocated to a process. So what do we do over here is, don't worry if it doesn't make a lot of sense right now. When we take an example, it will make absolute sense. Work plus what has been allocated to that process. And since the process is finished, now you will mark finish of I is equal to true. Okay. Now, basically, when you find the unfinished resources, unfinished process, right? When you find the unfinished process, the resources are allocated to the process, okay, and the process is marked finish. All right. Now, after this, repeat the loop. The loop is repeated from step 2 to basically check for the same. Loop through step 2 again, and this process you have to do for each and every resource. And the last step over here, right, that basically means if finish of I is true for all I, that means the system is in a safe state. This basically means, that means all the processes are basically finished. Okay. System is okay. That is what the overall idea is. But also understand something very important over here, which is that since you are actually, I would say, going through all the matrices again and again and doing it, it can actually take a time complexity of m into n square operations to actually decide whether a system is in safe state or not. Okay, but that is what the overall idea is about safety algorithm. Next, let's talk about the request resource algorithm. Okay, so the next algorithm is resource request algorithm, and it is mainly used to determine whether the request for a resource by a process can be safely granted or not. Okay, So let request of I be the request vector, okay, for process I. Okay, we have the request of I array, which is basically the request vector for processes pi. Now, if request of I, basically I comma j over here, is equal to k, and what was the, we are creating a request vector for every process I, okay, and if request of I comma j equal to k, that means that the process pi basically wants k instances of resource type rj. This is very easy to need and available. So if we have request comma j, this is, so we basically have a request array. That means, this means that process pi request k instances of resource rj. That's what it typically means. Okay, and when a request for resources is made by process pi, the following steps needs to be taken. Okay, first of all, you need to make sure that whatever is requested by the process I, that is in the row request of I, should be less than need of I. Okay, otherwise, if that is happening, then you go to step 2, otherwise you raise an error. Okay, since the process has exceeded its maximum claim. Okay, the process said I need 4 more resources. Okay, it was initially asking for 10, now it got allocated 6, now the need is 4 more. Okay, but now it's requesting for 5. That is wrong, right? You need to raise an error in that condition stating that the claim is exceeding. Second, if request of I is less than available, that means you are requesting for 4 resources and currently 5 are available, then that is fine. You can go to the next step. But if all the resources are not available, you will have to wait. Okay. And the third is, have the system pretend, right? You are going to pretend that the system has allocated the requested resources. Now, for a particular process, if the operating system has actually allocate the resources, now it has less resources present, so that is why the available resources would be available minus request. So initially I had 10, now I gave away 5, so I only have 5 resources available. So you need to update that. Second is allocation. Okay, initially you allocated, let's say, 4 resources, but now the process asked for 3 more and now you allocated 3 more. So the number of allocation basically increased to 7, 4 plus 3. And the last is need. Initially it was requesting for 4, right? And we basically allocated 3. So the need is still for 1 more. So initially the need for 4 was for 4. Now 3 got allocated. So it's 4 minus 3, 1. That means 1 more resource is also, 1 more instance of the resource is still required. Okay. And after this, if the resulting resource allocation state is safe, the transaction can be completed and the process pi is allocated its resources. However, if you go to an unstayed safe, then the process will have to wait, right? And the old resource allocation state will be restored. Okay. So you'll go back to the previous state. You will simply roll back. Okay. Perfect. Now let's go ahead. Now with the correct understanding we have for the safety algorithm and the resource request algorithm, we can go ahead and actually take a look at an example to fully understand it. There might be some scenarios where you may have some questions that you want to ask, but after this it will become absolutely clear. So here we are going to have 5 processes. Let me write this all down. And you have 3 resources, 5 processes, 3 resources. Okay, resource A has a total 5 instances, resource B has a total of resource A has 10, resource B has 5, and resource C has 7. Okay, and at t is equal to 0, the system looks like this. So you need to make all the matrices first. First, I am making the allocation P0, P1, P, or how do you want to do it? And this is R1, R2, and R3. Okay. And here this is, or the names are ABC for resources. And here this is 0, 1, 0, 2, 0, 0, 3, 0, 2, 2, 1, 1, 0, 0, 2. Okay. Now these are the allocation ones. Okay. What is the allocation one? Means that currently what has been allocated, and these are the max one. It's 7, 5, and 3. 3, 2, 2, 9, 0, 2. Okay. And then we have the available instance of the resources. This is what the snapshot of the system is. Okay, just to reiterate, what is allocation? Allocation defines the number of resources of each type that has currently been allocated to every process. So every process has these much resources allocated. Max is what is the maximum they can ask for. Okay, and available is what is the instances of resources currently available. Okay, so what you will do over here is you need to answer the following questions using the banker's algorithm, and the questions are, first question is what is the need matrix? So सबसे पहले you have to find that out. That means how many resources are required. Second, you have to find out, determine if the system is in safe state or not. Okay. And what will happen if the request for any resource is basically granted immediately. So what we will do is, first we will find out the need matrix over here. Okay. And if you remember the formula for the need matrix, it was that it's going to be an n cross m matrix, and the need for any particular row is basically for the max of I minus allocation for I. Correct? So I think we can make it here only. So we have need, okay, for A, B, C, and then we have P0, P1, P2, P3, P4. So this is 7 minus 0 is 7, 5 minus 1, 4, 3, 3 minus 2, 1, 2 minus 0, 2, 2 minus 0, 2, 6, 0, 0, 0, 1, 1, 4, 3, 1. This should how the need matrix should look like. Let's quickly verify. 7, 4, 3, 1, 2, 2, 6, 0, 0, 0, 1, 1, and 4, 3, 1. Okay. Once you have the need matrix, now you can apply the banker's algorithm. Okay. We know that the available resources over here is what, 332, right? Now we check basically see if these resources can be allocated to any process which has this availability. Okay, so we go step by step over here. So for process P0 over here, right, what you will see is you will see its need matrix. So the need matrix requires 743 as the instances of resource ABC, but we only have 33 2 available, okay, which means that we cannot satisfy the request of process P0. So what we do is we actually now go to the next process over here, which is this 122. Now basically we require 1 to 2 instances of resource ABC for process P1 and we have 332 available. That means we can actually satisfy the request. Okay, that means we can satisfy the request, meaning that the resources it was currently holding will also be available now. So that means this request will be satisfied and the total available resource, this will now also go into available. So now the available resource will be 5, 3 and 2 because this resource or allocation of 2 instances of resource A also got finished. Okay. So with this, what we've done is this is the new state of the available process and this process is basically marked true because it is finished. Now you go to the next process. Here we require 600, correct? And we do not have 600 available because resource A is not satisfying and we do not do partial allocation. So we move to the next process. Here we require 011, okay? And 011 is possible. So this process will be satisfied and its holding resource will now be available, which will be 211. That means 7, 4 and 3 will now be the next set of available resources. Okay, and process P3 is done. Next we go to the next process P4 and now for P4 also what you can see is this request can be actually satisfied. So this is marked true and its available allocated resources will now be available. So this is 7, 4 and 5 now, which is the next set of available resources. Okay, here for 431, right, which was I would say basically required, now it is available. So currently the available set of resource is 7, 4 and 5. Okay, now you've done with the last process. Now what do you do is you go back to the uncompleted process again. So P0 was uncompleted and now you can see that P0 can actually be completed because we require 7, 4 and 3 and we have 7, 4 and 5. So its holding resources now will also be available. So we have 7, 5 and 5 which is available and this is marked true. And now with this is the process we came over again, which is P2 and this is 600. This can also be done. So its holding resources will now be available, which is 10, 5 and 7. Okay, and in the end what you can see is we executed the banker's algorithm to find the save state and the save sequence along with it, which is P1, P3, P4, P0 and P2. Okay, and this would be the save sequence over here. Okay, and if you do execute the, I would say, the request in this particular format, you will be able to execute all the resources. Okay, and that's what the overall idea was about this. So you basically use this way of finding the save state of the algorithm and check if the resource allocation can be done or not. Okay, so that means you see what the resource basically needs more. If you do have enough resources, that means that process will be completed and the resource it was already holding will now also be available. That is why if you will see over here, initially we had the set of available resources, correct? And now whenever our allocation was done, the allocated resources for that process I was now also available and used to get added to work. Okay, and that is what the overall idea is. Okay, and now the third part for this could be that you can actually see that if I want to, let's say, process a request for 102. Okay, initially if you remember over here, right, when we came to the need matrix, let's say we also have to answer the question where can we grant the request for the resources 102, right? We will check that the available requested is for 102 and we have available for 332. That means the allocation can be actually done over here. Okay, so this is how you have to apply the banker's algorithm and basically solve the questions. So banker's algorithm basically helps you to take care of the fact that whether the system is in a safe state, and it also checks whether the allocation of the resources can be done or not. Okay, and that's what the overall idea is behind this concept. Okay, I hope this is clear to everyone. Banker's algorithm, I'm saying again and again, is a very, very important part. And bankers questions on banker's algorithm, you can assume also are very, very common. So it's equally important that you have a good understanding of banker's algorithm and you can devise all these steps. Make sure you go through all the algorithms again. Okay, if you want, you can take another example also and then maybe fully understand and foolproof on the concept, right? And then move ahead in this idea. We can take one more example also, in fact, in order to just to be sure if we understood the idea or not. Okay. So let's say we have here a processes. I'm taking example online and then we are going to solve it. Just give it a second for it to load. So we basically have the processes P1, P2, or sorry, let's take P0 only. Okay, and then we have A, B, and C. We have over here 1, 1, and 2, 2, 1, and 2, 4, 0, and 1, 0, 2, and 0, 1, and 2. Okay. So this is the allocation matrix. Okay. Then we have always the max matrix. For the max matrix, you have P0, P1, P2, P3, and P4. A, B, C. Over here we have 4, 3, 3, 3, 2, 2, 9, 0, 2, 7, 5, 3, 1, 1, 2. And then we have the available for this, which is 2, 1, and 0. And remember, always the first step is to first make the need matrix. The need matrix is A, B, C. So just do max minus allocation. 4 minus 1, 3. 3 minus 1, 2. 3 minus 2, 1. 1, 1, 0. 5, 0, 1. 7, 3, 3, 0, 0, and 0. Okay, so this is what our need matrix would really look like. Now we check and need to find the save state and the save sequence. We have 2, 1, 0. Can we execute process P0 over here? No, because the need is more and the availability is left. We have P1, 1, 1, 0. Can we actually do this? Yes. So once you execute this process, which is the P1 process first, its allocated resources will now be available. And now we have 4, 2, and 2 as the available set of resources. Now we go to process P2. Can we execute it? No, because A resource is not available. P3? No. P4? Can we do that? For P4? Yes, we can do that. So that means it does not require any more resources and its available resource was what? 5, 3, and 4. Okay. Now this is also available and after P1 we did P4. So far P1 is done and P4 is done. And then we go back to P0. We have 3, 2, 1. Can we do this? Yes, this process can be executed over here. And its available resource was 1, 1, 2, 6, 4, 6. Okay. Now this is the new set of resources which are basically available. Okay. So we have we did for over here P1, which was needing over here one more resource in this case. So we had 5, 3, and 4. Okay. And you can basically form any ordering you want. Okay. Now P0 process is also done with this. Next, we basically go to the process P2 P2 is 501, so this can be done. So if I am executing P2, its allocated resources 401, which is 10, 4, and 7. So now we have 10, 4, and 7 available, and we executed P2. Remember, there is no one unique sequence. There can be multiple. Okay. And then we have P3, which can also be done now, and its available resources 10, 6, P3, 7. So that is also done over here. Okay. And we basically have all the available resources. And this would be one of the safe sequences for the execution of all the processes. Okay. And that's what you need to keep in mind as well whenever you are doing this. All right. Okay then, I hope this is clear to everyone and you were able to understand everything as well. And now I will meet you in the next video. Thank you. Bye.